0 to 2. This is the 0 right here. Of what? 2r cubed minus r to the 4 distribution. The r, okay? The first one right here is just 2 pi. This integral is what? R cubed is 1/4 times 2 is 1/2. R to the 4 minus 1/5. R to the 5th. And this run from 0 to 2. Okay, and then plug in the numbers. You should have the answer. 2 pi outside, 2 here, 2 to the 4, 16 divided by 2 is 8. 2 to the 5th, 16 times 2 is 32 over 5. So minus 32 over 5 right here, and then of course plug in 0, they're all 0. And simplify. Okay. Is 40 minus 32 is 8 over 5. So 2 pi times 8 over 5. I think this is what? 40 over 5 minus 32 over 5. Yes, 8 over 5. And this is 16 pi over 5 should be the final answer. All right. So the tricky part is how to interchange from one variable to another variable with some boundary. Okay, but you draw the picture is going to help. And then after that, just be careful. Be very careful with your algebra, with your calculation. Okay, and you have it. Next, let me move on to another type of triple integral. Last type. This type, you see the box B, the box, like a sphere. Okay? And of course, you can use what? Rectangular coordinate dx, dy, dz, or you can use cylindrical coordinate r, d theta, dz to solve. But it turns out it's not as sufficient, it's not effective as the third type of coordinates that I'm about to show you right here. All right? So for this one, it's called the spherical coordinate. Spherical. Spherical coordinate. Okay. So again, if you have a point on the x, y, z plane, x, y, z, you have a point P right here. Okay. So how do you represent the point P on the xy plane? You're going to use three things. Rho right here represent the distance to the origin, directly to the point P. Okay, and this is the angle from the z-axis. Angle from the z-axis. This basically look the notation that the book used. I'll try to use the same thing. Oh, this is called phi, I think. Okay, and this is the angle theta, as we know already, in the polar coordinate. Okay. So the point P can be represented with three things. Rho, make sure that I write the same order as the book. Rho, and then theta, and then phi. By the way, I usually call it phi, right? But in here, like P, and we call it pi. This is P like pi, so this is phi. All right. So, if you have a triple integral where the box being, I think of it like a ball bead, okay? It's a ball, but looks like a round shape. And the triple integral can be written this way. Integral, integral, integral f of x, y, z is now become rho sine theta, and then, oh, I'm sorry, sine cosine theta. Make sure, let me double check I got it right. Okay? And y is rho psi phi, and then sine theta, and then z is rho cosine of phi. Okay? And dx, dy, dz now becomes This is see me in the rho square sine of phi d rho d theta and d phi. Hopefully you see on the board, right? Okay. Now let me explain to you why you have that. Of course, the integral right here, rho run from say rho 1 to rho 2, and then theta run from theta 1 to theta 2, and then phi run from say phi 1 to phi 2. Okay? It could be constant, could be a function. Let me explain how we have that. Okay, let's talk about z right here. This is z. Okay, this angle is phi. So z is up here. Z. And we have a right triangle right here with the hypotenuse rho. And this angle is phi. And z is this. Okay, so adjacent over hypotenuse z over rho is equal to cosine phi, right? This triangle. Let me draw this down here. Okay, this is your z. This is rho. This is the angle phi. So adjacent over hypotenuse is cosine of phi. Of course, you can calculate z in here is equal to rho times cosine phi. This is what we have right here. Okay. And now when you project the point P down to the plane, this is R, that what we're talking about in the polar coordinate. And you can calculate R using the right triangle. This is the rho that you have in here. This is Z right here. I'm talking about this rectangle right here. And this is R. This is angle is what phi. Oh, this is phi. So what? Opposite over hypotenuse is sine of phi. So what? R over rho is equal to sine of phi. Okay? So R is equal to rho times sine of phi. Okay? And of course, go back to in here, it's going to be polar coordinate. F is equal to R cosine theta, which is rho sine phi cosine theta. Okay? And then Y is R sine theta. We just learned polar coordinates. R is rho psi phi, and then sine theta. Okay? And you see in it right here, the x, dy, dz will change to, I did not remember, so I had to look at the book, but I'll show you the formula how we can change, because actually you know the general formula and you don't have to memorize everything. To rho square sine phi, d rho, d theta, d phi. Okay? And by the way, Pythagorean theorem applying in here, z squared plus r squared equal to rho squared. I need some room to write. Let me erase this part. Z squared plus r squared equal to rho squared. And you know what? R squared is just x squared plus y squared we had before, so z squared plus y squared plus x squared is equal to rho squared. Pythagorean theorem again. You have this. Okay, so anyway, the whole thing about the last section that we're going to cover today, 15.8, triple integral in terms of spherical coordinate. You have triple integral if the box now turns out to be a ball, circle, right? And then instead of using dx, dy, dz, you change to rho, theta, this is rho, okay? And this is theta, and this is phi, okay? Okay. You change to rho, theta, and phi, I claim a many problem. It's gonna be a lot quicker. Again, depends on the shape of that box that you have. Is that a lot of angle? Is a lot of straight edge? And depends. You choose the appropriate coordinate system to solve. As usual, let me give you an example. Okay, I see example number 3 in the book, so let me just copy the example 3 down up here on the board. evaluate this triple integral. 1, 2, 3 over the region B. Let's see, the box B. E raised to the power of x squared plus y squared. Oh yeah. X squared plus y squared plus z squared raised to the power of 3/2 dv. Okay. Where b is a unit ball. This is b. X squared plus y squared plus z squared equal to 1. See, this is the unit ball sphere. Of course, this is the example. Section 15.8, so they have to give you something that's obviously the spherical coordinate is going to be a better choice. But assuming that you want to do it using the x, y, z coordinate like what we had before, then of course you can do it, convert it. And this is what you should have. You do x, y, z. This is the ball, right? The upper half is the upper sphere, and then lower half is the lower hemisphere. The south one, the north one, in terms of z. So solve for z. You got z equal to plus or minus square root of 1 minus x squared minus y squared, right? The upper one is plus, the lower one is minus. I'm just trying to rewrite everything in terms of x, y, z, okay? I'm not going to do it that way to solve. I'll do spherical, of course. So the most inside one for dz, this is e to the x squared plus y squared plus z squared to the 3/2, I mean. Z going to be from what? Negative square root of 1 minus x squared minus y squared over positive square root of 1 minus x squared minus y squared. Okay? And if you project the whole circle down to the xy plane, you're going to have a circle, okay? A circle of radius 1. And this, in terms of z again, the circle of radius 1 is going to be what? X squared plus y squared equal to 1, right? This is the x-axis, this is y-axis. You project the whole circle down to the xy plane. So y is equal to plus or minus square root of 1 minus x squared, negative square root of 1 minus x squared, over positive square root of 1 minus x squared, and then x run from negative 1 to positive 1, 1 to negative 1 to positive 1. What did I say? dz, and then dy, then dx. This is what you should do. You have to do if you do Cartesian coordinate, rectangular coordinates. Okay. You see, the boundary is not so nice at all. Okay. I'm not going to do that. So instead, we're going to use spherical. What do we know about spherical? I know that x squared plus y squared plus z squared, x squared plus y squared plus z squared is just rho square. Okay? And I know that dx, dy, dz will change. I say dz, right? We change to what? Rho square, psi phi, and then d rho, d theta, d phi, and it's all constant for the ball. One thing that I want you to pay attention, talk about the spherical. We write it one more time. Point P right here. The angle from here to here is phi. Okay, and then down here, the angle here is theta, and this is rho. So rho is the radius already. The angle of theta is going to go around the xy plane is going to be from 0 to 2 pi. But the angle phi right here, you only need what? From 0 from here all the way to 180 degrees. So phi, I claim this is going to vary all the way from 0 to 1 pi. Okay? That's point B. Doesn't matter which way, up and down. You can rotate it around. Okay? The whole circle around the xy plane. All right. So this one, if you convert it into the spherical, it's going to be like this: triple integral a to the power of rho to the 3/2, right? This is rho square to the 3/2. So it's just rho cube. Yeah? Because what? Rho square raised to the 3/2 is just rho cube. That will cancel out. That's what I have, right? Then I got rho square. I got sine phi, and then d rho d theta, d phi, they're all constant, I think. And this is a sphere already. So the radius r is 1, so 0 to 1 for rho, and theta is from 0 to 2 pi, and phi from 0 to 1 pi. Let's just give you an explanation about the phi, just 0 to 1 pi, okay? And then integrate this, okay? Inside out, I think this is separable, right? Yeah, all variables separate. So you can rewrite this way, be easier. Integral from 0 to pi, this is for phi, and I got nothing, so just d phi, right? And then integral from 0 to 2 pi, theta, what do I have a theta? Oh, I missed the sine phi right here. So sine phi, d phi. Okay? And for theta, do we have theta? So nothing. So this is theta, d theta. Okay? And then integral from 0 to 1 of e to the rho cube, then times rho square in front, d rho. Okay? So 3 separate single variable integral. And this one is what? Derivative of cosine is negative sine, antiderivative negative cosine of phi run from 0 to pi. And this is just 2 pi in here. The last one right here, you do a u sub, u equal to rho cube. So this is 1/3 e to the rho cube, and this run from 0 to 1. And of course, plug in a number, you guys have the answer, right? Cosine of pi is -1. Cosine of 0 is 1. So negative 1 is 1, so this is 2, I think, right? And this is 2 pi, and this is 1, so e, so 1/3. So answer is going to be 2 pi, so 4 pi over 3 times e minus 1, because e to the 0 is 1. Yeah. That will be the final answer. Okay, let me save the last couple of minutes to show you in general how you convert from one set of coordinates, say dx, dy, dz, to r, dr, d theta, or d rho, d theta, d phi, whatever you have. And again, this formula is very general. It means what? You can apply for what? 4 or 5 variables. That's fine. Not just 2, not just 3. Okay, and this is the lecture. Objections, okay? Something for Jacob here. Right? Let me see how it was stated. Say you have a function from x, y, f(x, y), right? Of course, this is going to be dx, dy. And you want to change to a new variable, say x in terms of uv. Of course, y in terms of uv. In our particular problem, we have x in terms of r and theta, and y is in terms of r and theta. And I'll just write uv in general, just like in the Jacobian, how they write, doesn't matter. Okay? They got Jacob and they define this way. Partial derivative function x over u, partial derivative function x over v, and then do the same thing for y. Calculate determinant of it. Then you're going to have the quantity in front of the new variables. Okay, so let's go an example. I got x equal to r cosine theta, so u is like r, and v is like theta, and y equal to r sine theta. Okay. I'm trying to convert from dx, dy change to r, dr, d theta, and how it's going to work. First of all, we're going to do partial derivative. Dx over dr is cosine theta, dx over d theta, okay, partial derivative of r, partial derivative of theta, dx over d theta is negative r sine theta, because the derivative of cosine is negative sine, and then dy over dr, dy over dr is sine theta, dy over d theta is r cosine theta. Okay, so my Jacobian is gonna be what? The x over dr is gonna be cosine theta, x over d theta is negative r sine theta, dy over dr is sine theta, r over d theta, dy over d theta is r cosine theta. And if you took pre-cal already, this is a 2x2 matrix, and you want to calculate determinant, right? A times B minus B times C. So, determinant, you know this way then. It is what? R cosine square theta minus with minus become plus. R sine square theta, you add them up, it's R cosine square plus theta plus sine square theta. And this is equal to R. Okay. So what? dx, dy, we change to what? The absolute value of Jacobian, dr, d theta. And the absolute value right here is R. This becomes R dr d theta. And that explains the whole thing. Similarly, you can try this for 3 variables as you have before. So if I got x is that, y is that, and z is just z, right? So you can do what? Jacobian gonna be the 3 variable, right? So x become what? UV w, UV w, the 3 variable, and then z is UV w. Jacobian now is a 3x3 matrix, right? This is dx over du, dx over dv, dx over dw. Same thing for y. This y over dv, and then dy over dw, and then dz over du, dz over dv, and dz over dw. Then you have a 3x3 matrix, and the same thing. dx, dy, dz will be changed to the absolute value of Jacobian times du, dv, dw. Okay. This is the J that you have. Okay. If you want to change. To convince you, let me try one more. 3 variables, right? If I got x is r cosine theta, y is r sine theta, and z is just z, like a cylindrical coordinate. Okay, so dx over dr is cosine theta, dx over d theta is dx over d theta is negative r sine theta, and then dx over dz, third variable z, right, is 0. Similarly, dy over dr is what? Sine theta. Dy over the theta is r cosine theta, and dy over dz is equal to dy over dz is 0. Okay, and for z, dz over dr is 0, dz over d theta is 0, and dz over dz is 1. Okay, so your Jacobian gonna be like this. Plus 1 negative cosine theta, positive cosine theta, negative r sine theta, and then 0, and then what? The second one for y, sine theta, r cosine theta, and then 0. Last one going to be 0, 0, 1, And again, determinant of this matrix, the same thing is right here. And then time 1, you use the last row or the third column. The determinant of this is going to still R. Okay. Or you can convert from x, y, z to what? D rho, d theta, d phi, and use x equals rho sine cosine, y is rho sine cosine here, and z is rho cosine, and calculate Jacobian matrix. You should have the answer. Okay, this is gonna be a little bit of work, so the book hide it from you. Just give you the answer. I show you the way to get there. All right, consider that's an extra problem for you guys to check out. Okay, let me stop the video clip right here. Thank you for watching, guys. In the next video clip, I'll start chapter 16, and as usual, any question, because I know it's count 3 and a lot of work, so it's not easy. Please feel free to ask. Many of you asked, but many others still haven't asked yet, so I assume that you guys do well. But if I say, if you have any problem, please don't hesitate to ask, okay? I'm here to help you out. Thank you, and have a good day, everyone. Bye-bye.